All right, students. Hey, well, it's Tuesday night, and you took the exam today. And I've been pretty busy, but I've been wanting to make a solution here for you so you can kind of go through and kind of both self-grade yourself and maybe more importantly, see what you did wrong. And so this is the at least the first three questions, and I got the other ones over here. We'll go through all of those, and some of these are pretty hard, and some are a little more straightforward. And so let's just kind of work through this. I'll start with the first one here, and you can kind of see what you might have missed and what you kind of overlooked. This first one I hope was pretty straightforward. You'll probably recognize it right away out of Coulomb's law. We got an electric field. We've got the movement. It also then goes back to physics 121 since we got motion and distance involved. As you know, a lot of those problems did that with us. All right, so let me just kind of go through here. I'll put here number one while I make the solution set here, and hopefully this will be helpful to you, and give me a solution set so I can start grading these tomorrow, although probably won't have too much time, so probably have to do most of it over the weekend here. But it says a proton with a charge of, okay, and a mass of, enters the space between two parallel plates. The proton is traveling parallel to the plates when it enters with this speed. If the top plate has an area of and a charge of, how far horizontally does the proton travel as it travels 1.20 millimeters vertically upward? Go ahead and assume it doesn't hit the plates. Okay, so it's going to do something, like this. And so there's the question, how far over did it go? So question mark. How far horizontally, now that it has bent, and I put it upward because it's a positive charge, it's a proton, and the bottom plate's positive and the top plate's negative. So there'd be an electric field pointing vertically upward, and that would push it upward. Okay, and then there's some vertical distance, and that vertical distance is given by 1.20 millimeters. All right. By the way, this is a good problem because we're going to do exactly this later on as we understand how a very important piece of equipment works called the oscilloscope in the lab. Okay, so keeping that in mind, I guess the first thing that comes to my mind and related to this semester is that the force on this is the charge of the proton times the electric field. And the second thing that comes to mind is that the electric field is the surface charge density over epsilon naught. So I guess this right here is from chapter 23, and this right here is from chapter 24. So putting those two together, I could then figure out what the, maybe I'll do it step by step. This is the electric field. Let's do that one first. So I'll just put a Q and leave the charge alone here. Let's do the electric field. So the electric field is the surface charge density. They tell us that there is 2 nano, 10 to the minus 9, spread out over 0.155 square meters. So that's the surface charge density. And the permittivity of free space is the 8.85 times 10 to the minus 12. So I'll start there. That'll give us the electric field. So let me take the 20 nano and divide it by the 0.115. And so there's the sigma, the surface charge density. Let me divide that then by permittivity of a free space, and about a 14,000, I'll just call it 580 newtons per Coulomb would be the electric field. Okay, so now if I take that field and multiply it by the charge, that'll tell me how much force is on this proton. So times 1.602 times 10 to the negative 19. So this is 2.33 times 10 to the minus 15 newtons pushing it up. So I might say that's the first step. That's how much is pushing it up. Now, the rest of this really goes back to physics 121. So if I was gonna, do kind of a projectile motion problem, I would, say, okay, x and y components are separate. And in this case, the change in y would be the initial velocity in the y times time plus 1/2 acceleration in the y direction times squared. And so we are going to go up, what did it say here, 1.2 millimeters. So let me write that in meters, 0.0012, okay. It goes parallel to the x-axis, so it's got no speed in the vertical direction when it enters. Then we've got this 1/2, and now we have the acceleration in the y direction. So that would be the force we just talked about in the y direction divided by the mass. So there's Newton's second law. So I guess that goes back to chapter 5 of our books, whether you're looking at Survey or OpenStack, same chapter number. And then t squared. So the force we just did up there. And so if I put in that force and divide it by the mass of the proton, 1.67, I believe 2, times 10 to the negative 27. That number right there, 1.6, oops, I forgot to hit divide. Let's try that again. So here's the force, inner, and divide by mass of the proton. And we get an acceleration of, what is that number? 1.40 times 10 to the 12th t squared. So there's the acceleration. And an important part here is then to get the time. So I can take the 0.0012, multiply it by 2, divide by the acceleration, that'd be the time squared, take the square root of that last answer, and we're looking at a time of about 4.14 times 10 to the minus 8 seconds. So that's how much time it takes for this proton to get pushed kind of upward the 1.2 millimeters. Okay, so then finally, again, more about physics 121 at this point, everything from here on. But we can come back over here and say, okay, the change in the x position is, again, the initial velocity in the x direction times time plus 1/2 acceleration times squared. There is no field, and therefore no force, and therefore no acceleration in the x direction. That was, I guess, really part of this semester where we're talking about a field pointing straight upward between our two parallel plates. So then we can just put in the initial speed in the x direction, which they give us as 6.5 million meters per second. And this time as 4.14 times 10 to the minus 8 seconds to get our distance. So I've got the time already in my calculator. Let me just take the speed of 6.5 million meters per second and coming up with a distance of about 26 centimeters. So 0.269 meters. Yay! So there is this one. And like I said, hopefully a little straightforward towards you. I mean, this really wasn't anything more than just our first step with the electric field. I guess it did go into chapter 24 a little bit. Then the rest of that is stuff that hopefully you're still remembering from physics 121 and our kinematics here. So there we go. In fact, these numbers are really nice numbers. They're very realistic numbers. They're stuff that we're going to see, as I mentioned, coming up in a lab with the oscilloscope. It's a little ways off because we learn a little bit more about magnetic fields. So we've got a ways to go before we kind of get to actually seeing this in action. But these numbers are very realistic numbers. Their speed may sound high, but these are little things. Their accelerations may sound high, but again, these are little things. And so very little charge, 20 nanocoulombs over a pretty big area, then results in these things getting pushed around really well. Although I guess I should say we're not going to be pushing protons, we're going to be pushing electrons. A couple labs we push electrons around. Okay, so let me move on. Hopefully, like I said, you did well on that, and hopefully that one got you a little bit going and warmed up and was under the 25 minutes. You have time for 25 minutes for each problem. So it looks like I'm into about 11 minutes. So with that, I'll go on to number 2. And number 2 is kind of a two-step process. It looks like the first part of number 2 is pretty straightforward, but B is the little harder one anytime we have a charge that is spread out. So this is, again, to kind of get you warmed up and kind of see if you kind of remember the whole idea of potential and how we apply conservation of energy. So in that sense, it goes back to Physics 121. But the step up in part B is where we take charge number 1 and we spread it out a little bit. So that's gonna be where the work gets hard in B. But so let's do A first. And if you read it here, it says a movable point charge of mass, and so they give it in grams. Be careful with that, not kilograms. And a charge Q2. So here it is. Here's the movable one, and it's placed at rest. And then right here, 12 centimeters from a fixed point charge of 65, it is released from rest. So good, so they tell me rest twice. Okay, so this one starts at rest. How fast is the movable charge moving after it has moved 1 meter or 100 centimeters away? So now the total distance is 112 centimeters. So this one's going to get pushed. So hopefully this just sounds like the ones that we did in chapter 25 about the potential. We kind of argued here that, if I can make my little sketch here, that the nice thing about potential is that it leads directly to potential energy. And the nice thing about energy is it really directly using the principle of conservation of energy to a velocity. And I kind of like to make a bigger diagram here. That says something like this. Where this part is really our kinematics. This is our connection between position, velocity, and acceleration. This was all part of chapter 1 through 4 in Physics 121, then chapter 5 and 6, and then the energy right here, chapter 7 and 8. So that's our 121, and what we've added to it here in chapter 25 is this, the idea of potential, where then you could get potential energy. So U for energy is the charge you place there times the potential. And the potential for a point charge is KQ over R. And let's do that, and we'll do that with A. And by the way, not needed for this problem, but the other thing we did was, Coulomb's law, add up the electric field from a point, and so KQ over R squared. You do that for a bunch of points, you can get the net field, which gives you the net force, which you integrate to get the acceleration. And so we could do this stuff, and that's what chapter 23 was about. And of course, chapter 24 was about this step, where we had an alternative to Coulomb's law, which we call Gauss's law. And you could even argue they're kind of the equivalent, but it's kind of a different technique. It's a more of an argument of symmetry in a mathematical surface. So it's a brilliant idea by Gauss, so hence Gauss's law, but it leads again to finding the electric field, which then force is the charge times the electric field. And so you have these alternatives. So I'd say this is chapter 23, this is chapter 24, and this is chapter 25. And this is the path I'm going to take. I'm going to take the potential here in chapter 25. So let's do that first, which will then give me the energy and the principle of conservation energy going back to chapter 8, and then get the velocity. So that's the pattern here. All right, so let me do that. And so we would ultimately, we're going to need something like this. The initial kinetic energy plus the initial potential energy is then equal to the final kinetic energy times the final potential. And this right here is where I want to get started. So this would be Q times the initial potential, and this right here would be Q times the final potential. So let's just calculate initial potential. And these are point charges here in A. So this is KQ over R, and I'll put R initial. So this is 9 times 10 to the 9th. And the potential, let's come back here. It's the potential that is created by charge number 1. Of course, we're going to put charge number 2 in its position. So maybe I should put, this is going to be number 2 that we are going to then put in a potential that is created from number 1. And so I'm looking for the potential that's created from number 1. So I need the charge from number 1. Now, the charge from number 1 was what? 65. So 65 microcoulombs goes here, and we are starting at 0.12 meters away. Now, I'll just go ahead while I'm here, and I will do the final potential. And then again, that would just be KQ over R final. So this would be 9 times 10 to the 9th. And again, the 65 microcoulombs. And then, of course, this Q2 has moved away. So now we're looking at a distance of 1.12 meters. And so that's the part related to this semester. How do you calculate the potential? And then the potential energy. And then, of course, we'll go into Physics 121 and use this right here, the conservation of energy, to figure out the speed here. Okay, so let me take this 9 times 10 to the 9th times 65 micro, all divided by 0.12. And this would be about a 4.875 times 10 to the 1, 2, 3, 4, 5, 6 volts. And this other one, I guess I could save myself a little bit of work if I just re-enter and change the denominator. And so we're looking at 5.223 times 10 to the 1, 2, 3, 4, 5 volts. And so now I can do my Physics 121 stuff here and say, okay, well, the initial kinetic energy is 0. They say it's at rest. And so this initial energy coming back to here would be the charge I'm going to put there times the potential. So it would be charge number 2 times the potential of number 1. Let me just come up here and grab the potential of number 1 and multiply it by charge number 2, which is that 38 microcoulombs. So this is about 185.25 joules of energy. And then the final kinetic energy would be 1/2 times its mass, and since joules have buried inside of it kilograms, let me make sure that for final kinetic energy I put the mass in kilograms, okay? and then the final speed squared, and then times the initial potential, which energy. So let me come up here and get the initial, or the final potential, sorry, final potential, hit enter, and multiply it by that charge number 2, which again is that 38 microcoulombs. So this is going to be about a 19.85 joules. And then finally, we can get a speed out of this by taking this number, 185, subtracting that number. And so that's a change of about 165 joules. Then multiply it by 2, then divide it by 0.12345. That'd be the speed squared. So then let's take that and take its square root. And so we're looking at 857 meters per second. All right. So that's the idea. And so again, kind of summarize it. A lot of this is your Physics 121, your conservation of energy and getting the speed and looking at this diagram. But of course, the new stuff is right here out of Chapter 25. And maybe you remember from the video lecture, I said that why do we care about potential? Well, there's 2 reasons, and this is one of them. If we have potential, we can get potential energy and use conservation of energy to get the speed. Of course, remember there was another option, is we could take its derivative and get the electric field. And that's not part of this problem or any of the problems on the exam. So I'll just point it out, but we don't really need that here. Now, let's go to Part B. Part B is the same logic in terms of doing this problem, in the sense that I'm still going to follow this diagram, and I'm going to go to Chapter 25 here and say, okay, let's find the potential. And, of course, then we'll have an initial potential, which will lead to a initial potential energy, and we'll have a final potential which will lead to a final potential energy, and then we'll apply conservation of energy. So maybe I'll just start off again and write, okay, the principle of conservation of energy to get us started. But as I said right here, this right here is really about finding the initial potential energy, which we get from the initial potential. And this right here is about getting the final potential, which leads to the final potential energy. So all the steps here in B are identical to the steps I just did in A, except for we don't have a single point charge. So we can't just go back and do this. And so that's what's going to make it a little bit harder. So let's ask ourselves this question. Let's just say, you know, that we have this rod here, and we want to find the potential some distance away, x, when, say, the rod has a length of L. And its charge is also spread out uniformly. So let me call that lambda. And here's kind of the thinking on this. This was a homework problem. So if you want, I suppose you could just kind of look it up in your homework problem. I don't think it was in the textbook as an example. I did notice your textbook did something like this. They did take a rod and take the potential along its edge perpendicular to it. And so the formula you get from that's not quite the same. So don't just blindly plug and chug there, but you can go back and kind of look at what they did. But here's the thinking along their lines, is if you want to find the total potential, you just have to find the potential from a little piece and add it up. And maybe a little colored chalk or colored markers here would be good, but maybe I'll just kind of do something like this, and maybe actually, maybe for a little better understanding, why don't I call the distance away A? Because here's what I'm going to say. If I let the x-axis start here and go out, I would say something like this, that my first little green chunk of charge is a distance A away. And then as I add them up, I get to the last little chunk of charge, which is a distance of A plus L. So what I'm going to do then is to say, okay, what is the potential do I get from a little chunk of charge? And that little chunk's going to have a charge of dq. So using our formula for potential, coming back here, is I'm just going to take this little equation for a point charge and say, okay, a little bit of charge then would give you a little bit of potential. So I just have to kind of add it up, okay? Now, that's where things like charge density become real nice. So if you take a little bit of charge over a little bit of length, of course, that would be the same as the total charge over the total length. More on that in a minute. But let me use this one here first, and so I can just replace this with lambda dx. And then r is the distance away, and since it's just a straight line, it's not like the harder one in the book where they had to do Pythagorean's theorem. This is just a straight shot away, and so r would be some distance, which I probably should just call it x, and starting at a distance of x equaling to a and going to a plus L, which then of course makes a fairly easy integral to do. This would just be Coulomb's constant times lambda, and then I just have that integral of dx over x, which is ln, and so I'm going to have an a plus an L over an a. Okay, so there's how you get the potential. All right, so if I say, okay, what is the initial potential? I got Coulomb's constant, 9 times 10 to the 9th. I have the charge density of the rod. Well, here I'm going to come back and say, well, unlike before where I thought about it as a little charge over a little distance, I'm going to do the whole charge over a whole distance. All right, so for this problem, the whole charge was what? I tried to keep these numbers the same so it wouldn't be too confusing. The charge, yeah, so the total charge of 65 microcoulombs. So this is 65 microcoulombs, and over a rod that is a half a meter. So there's the charge density. Now, the A is the distance away, and the L is the length of the rod. So we start off with a point that is 12 centimeters from the end of the rod. So the 12 and the 50 make the 62 centimeters, starting at 12. So there would be the initial potential, and then this would be the final. So I hope you're kind of seeing that for part B. I'm doing exactly the same thing I did in A, with the exception being I don't have a point charge. So I have to find the formula for this rod. That's the only thing different. And so instead of using that formula for the points as I did in A, I'm going to be using this formula for the rod. All right, so the final potential when it moves away would be like this. It'd be the same charge density of the rod, but now, of course, let's see, we're looking at, I think it still moved a meter away. How fast is it moving after it moves 1 meter? So the A value here would be 1.12. Because it's the 12 and then it's moved a meter. Okay, it's 100 centimeters. Okay, and then the total distance, well, I guess probably easier just to look at this and add a meter to each one because it moved. So that would be a meter longer and that would be a meter longer. Okay, and so that's the final potential. All right, so if I grab my calculator here and put in these numbers here, 9 times 10 to the 9th times 65 times 10 to the minus 6 divided by 0.5, and then times the natural log of 0.62 over 0.12, we are looking at about 1.92 times 10 to the 1, 2, 3, 4, 5, 6 volts. And then over here, maybe I'll just do a re-enter. First numbers are the same, ln, and now we're going to have, and I'll just insert a 1, come over here, and insert a 1. All right, and go enter. And so this would be 7.09 times 10 to the 1, 2, 3, 4, 5 volts. Okay, so here's the part I was saying that's still the same. So we're going to come down here and put in our initial kinetic energy is 0, like we did before. And again, like we did before, let's just take the charge of this, the 38 microcoulombs, and multiply it by the 1.20 million volts. This right here would be the 1/2 times the mass again, 0.000 or 00045, final speed, and then plus this number. In fact, maybe I'll just work that number out. I still got that number in my calculator, so it's that volts times the 38 times 10 to the minus 6. So this would be about a 26.45 joules. And then maybe this number here, I can just go up and get it right there and multiply it by the 38 times 10 to the minus 6. And then this would be the 73.01 joules. All right, so let's see what this comes out to be. And let me just take a moment to say, well, maybe we should give this some thought, too, about what kind of number do we expect? You see, in part A, we got a speed of 857. And the difference between A and B is essentially we've took charge number 1 and it's the same magnitude, but we spread it out over a meter long. And what that means is a lot of the charge then is further away from number 2 than it was before. And because of that, there'd be less of a push or less of an energy. And because of that, as it moves away a meter, we would expect a lower speed. So I'm going to hopefully get a speed here that is lower than what we got in A. And that might be just a good way to kind of understand our numbers, what I like to call read our numbers. It's okay, what's going on here in this physical problem? And this problem is almost identical. The procedure is identical. The only thing different is right here, the formula for the potential. And of course, conceptually, we see that the charges is now spread out further away. So expecting a number less than 857. So let's see what I get. This is the 73 minus this. And so that is a change of energy here of a 46. I feel like I hit a wrong button somewhere. Is that right? 46. don't really like that number. Let me just check something real quick here. Because I had worked this out before. Let me try this one. This one doesn't seem quite right. Did I hit something wrong? 65 times 10 to the negative 6 divided by 0.1. Okay, and then times the natural log of 1.62 over 1.1. No, okay, I like that number better. I wonder what I did wrong. Maybe I'll have to go back and look at the video here. One, two, three, four, 5. All right, well, after I'm done doing this, I'm going to go back and look at the video. But I must have did something wrong. And I remember I messed up on my insert. So yeah, I'm sure I did something. And I guess I could scroll up and see what I did. I think... that's where I blew it. I copied the answer down, and that's my mistake. I tried to save a little time and got the wrong thing. All right, well, at least I see my mistake. So, and I'm glad I saw it before I got too far along here. All right, so let's try that again. That would be the final potential. So that means this number's wrong. Oh, no, that's initial. That number was fine. What was that number? 7301. The final would be here. So that number's wrong. Okay, so let me take that voltage and multiply it by the 38 times 10 to the negative 6. And so let me look at 16.4. So then 73.01, 16.4 is where I kind of hesitated because I was like, okay, I think the energy was in the 50s when I was talking with somebody about this. And I was like, okay, wait. All right, good. So I like that better. So that's the 50 has to equal 1/2 mv squared. Okay, so then times 2 and divided by 0.123, 45, and then the square root is 505, and that's what I remember getting when I was talking with somebody. Okay, good. So 505, and it is then less than the part A now that the charge has spread out. Okay, so this part B was, like I said, in some sense it was all the same, so maybe I'll say it was easy, but it's this line right here that you've got to kind of work out on your own. And that's what makes it a little harder. You won't find that equation directly in the book, although I guess if you look at the homework and the homework solutions, and if you remember doing it, you could have look at those up and kind of do a plug and chug. But for the most part, I wanted to put that there because all of A, you could just do plug and chug. You got that, you got that. I mean, they're all given, and really without much physical understanding, you can just plug and chug and get the answer. But this one takes a little more thought. And so it's this line that takes the thought right there. How do you get the potential along this line? All right, well, I hope that was helpful to at least one of you. Let's move on to number 3. Now, number 3, we've got our capacitors. I think of these first 4 chapters as the first 3 being really hard chapters. And now you're about to see some application chapters. And so this chapter here, 26, and then 27 and 28 are kind of all applications. Although 27 has the physics of what is the current and what is the resistance. But that's not too hard. But this 26 and for that matter 28 are the applications of science that we've learned so far. And usually the applications are the easier chapters. It's you know, because you've already learned it, part of it, and part of it is the tougher stuff, like the capacitance stuff has all been worked out already for you. Anyways, I say all that because I hope number 3 will come across as a pretty straightforward one. It's new material, so maybe it's not quite as easy as number 1, because number 1 was old material and just a little bit of new stuff. But this is all new but straightforward stuff here. So let's go ahead and give it a try. Although it too can be a little bit of a challenge, because we have to make our equivalent circuit. And so maybe the first thing to do, and for you guys on the video, I'm just going to redraw this. C1 here is 15 microfarads. C2 is 5 microfarads. And let me just pause while I'm drawing it. Notice that I drew a line straight from the 1 to the 2, so there's no place to go. So those two are in series. I'll keep that in mind. Then it goes here and it branches off. Okay, so branching off, that means not in series. So neither one of these is in series with number 2. In fact, this is labeled number 3 and has a value of 4. And this is labeled as number 4 and has a value of 1. And so these, 3 and 4 are not in series with 2. And for that matter, 3 and 4 are not in series with each other. However, you kind of look at this carefully. 3 and 4 are in parallel with each other. This is the part that I was saying. If you could, if they're connected with a wire, and you kind of draw it in a green color, you'll say that those two plates right here have the same potential. And maybe if we draw the other plate, and that's where it might be a little hard to see, because I've got a lot of drawing to do and a lot of bends to do, but there's nothing in between them. And so this, I'll call it the left plate of number 3 and the bottom plate of number 4. Those would be the same potential. So I've got like a green to a red on both of them. So that's the same voltage. So these are actually in parallel. So 3 and 4 are in parallel and 1 and 2 are in series. So when I make the next step here and say, okay, well, what's the equivalent circuit of this? You could either put 1 and 2 together first, or you could put 3 and 4 together first. It doesn't really matter. You're going to get the same thing. So I'm just going to put the 3 and the 4 together, and they're easy to do because you just add to get the equivalent. So the equivalent of 3 and 4 is a 5, and number 2 is still a 5, and this is a 15. But once I've done that, notice this, that 15 goes to 5 and this 5 goes to the other 5. These 3 are in series. So if I wanted to know the equivalent of everything, all 4 of these, okay, and so this circuit here is the equivalent of that one. And if I wanted to do a final step and say what is the equivalent of the equivalent, I could say what are these 3 equivalent to? And since they're all in series, I can go 1 over 15 plus 1 over 5 plus 1 over 5 and get to the equivalents of all of these. So let me do that. So I'll take the reciprocal of 15, also the reciprocal of 5, and also the reciprocal of 5. Now, don't forget this final step. This is really easy to do. But when I add those, I don't have the equivalent quite yet. I have the reciprocal of the equivalent. So one more step is to take the reciprocal and say then that the equivalent is 2.14. And I've been doing everything in units of microfarads. Okay. So that's the I'll call it the first major step, maybe half the problem right there, is looking at this. Here's the real circuit, here's an equivalent, here's the equivalent of the equivalent. And these equivalent circuits are very useful in the sense that they can lead to information about the real circuit. Because the real circuit, we are asked to fill in this chart. If we take the capacitors, 1, 2, 3, and 4, this problem asks for what is the voltage and what is the charge on each of these. And if you didn't kind of catch it in the lecture part of it, let's do that. Let's look at this circuit here, which I like to call the equivalent of the equivalent. Remember, this is the equivalent of that one, and this is the equivalent of that one. But let's look at this one for a moment. If we take a voltage here of 12 volts, and remember that charge is equal to the capacitance times the voltage, this equivalent of the equivalent, this one here is an easy one to work with because you know it's just hooked up to a 12 volts, so you know its voltage is 12, and you know its equivalent capacitance. So this is 2.14 microfarads for its capacitance, and its voltage is 12 volts. And if I multiply that together, I get a 25.7, and a farad, member, is a coulomb per volt, and so that will leave me with a coulomb, and I'll leave the micro alone, and so this is 25.7 microcoulombs. Now again, this is not the real circuit, so keep in mind that the whole reason of doing this is so that I can figure out the real circuit. So maybe comparing this to this and then back to the real circuit, what's really going on here? Well, the equivalent one is nice because this number here tells me how much charge then comes out of the battery and goes on to this equivalent capacitance. But if you take that logic all the way back to the real circuit to begin with, that would then come out of this battery, and then it only has one place to go, onto capacitor number 1. So that would tell me this must be the 25.7 in units of microcoulombs. So that's how this equivalent of the equivalent circuit can be very useful to the real circuit. Now, also, looking at the real circuit, notice that if that much charge went on to C1, it chased that much off this plate, I'll call it the right plate of C1, and then goes to the top plate of number 2. In fact, we said earlier 1 and 2 are in series. In fact, in the equivalent circuit, all 3 of these are in series. And one thing we know about series, because they're connected one to the other, and because of conservation of charge, they have to have the same amount of charge on them. So this is 25.7 also. So again, that's how this equivalent of the equivalent circuit can be useful, because it gives us information about the real circuit. Okay. So I've done, part of the chart here. It looks like there's 8 things I need, and I've got 2 of them once I've gotten to this particular point. Now, if you compare the equivalent circuit and the equivalent of the equivalent, you can see that this charge would be here, this charge would be here, and this charge would be here. So this one down here is the equivalent of these 2. So you know that these 2 add up to 25.7. So hopefully we can check our work and we're all said and done. Those should add up. Or put another way, each of these should be under 25.7. So, okay, that's nice. Now, maybe going back to just my thinking of, remember that capacitance is the charge over the volt, and if you ever know 2 of these, you know the third. And we're given capacitors 1 and 2, and we just figure out the charges on 1 and 2, so we should be able to also get the voltage on 1 and 2. So we would take the charge and divide it by its capacitance. So we've got the charge of the 25.7 microcoulombs, and so if we divide it by the 15 microfarads of number 1, the micro would cancel off, and we're looking at a 1.71 volts. And then likewise here, the 25.7 divided by the 5 would give me a 5.14 volts. So that's probably the easiest way to get 2 more on here. Now, here's a good place where we would want to look at the equivalent circuit. And I think we pretty much exhausted. We got these four from the equivalent of the equivalent. But if we come back here and focus on this equivalent circuit, we'll see that the three of these are each pushing against this battery. So the sum of these three voltages have to add up to the 12 volts. See, and we already got two of them, these two. So that means the voltage on number 3, and for that matter, number 4, because remember, 3 and 4 are in parallel. Okay, you can kind of say it this way, that if you go around this loop right here, 1, 2, and 3, that's got to add up to what you're charging it. Notice I did not say all 4 have to add up to 12, because I don't have to go through all 4 of them in order to get back where I started. So it's just through these 3. So the voltage on 1, 2, and 3 has to add up to 12. And then likewise, I could go around this bigger loop. This one plus this one plus this one pushes back against the battery. So 1, 2, and 3. These, the first one, the second one, and the fourth one have to also add up to 12, which is another way of saying 3 and 4 have to be the same voltage, which is another way of saying 3 and 4 are in parallel. So we've already concluded that. So what I'm going to do here for number 3 is take my 12 volts and then subtract off the 1.71 and then also the 5.14 and get myself a 5.15. And as we said, since they're in parallel, they're going to have the same voltage. So note again, I am not saying, never have, that all 4 of them have to add up to 12. It all depends on how they wire them. And so it's, this is wired so that 3 of them go around to make the battery, or these 3 go around to make that battery. So these 3 or these 3 have to add up to 12, but not all 4 of them. Well, and now we can finish the problem by, again, saying if you ever have any 2, you can get the third. And so the charge would be the capacitance times the voltage. So if we've got the voltage, we can just multiply by the capacitance, which is 4. And that would give me a 20.6 microcoulombs. And this voltage times 1 would be 5. I'll put 1.5 would then be the charge on that one. So that's the gist of it. You start with a circuit, you get its equivalent, and if need be, the equivalent of that one, and if need be, the equivalent of that one. Now, this one we only had to do the equivalent twice to get to here. But once you get down to here, it's an easy step to figure out a couple things, and then you build back up, going from the equivalent of the equivalent back to the equivalent, back to the real thing, and eventually you understand the real circuit. That's the whole point. These other ones, then you can kind of cross out that, well, those were just useful pieces along the way because they were equivalent and they helped us just analyze it. All right, so quite a few steps there, but everything was and new. Okay, so hopefully that wasn't too hard for you, but being new, it could have been. And then seeing whether they're in series and parallel is a little bit of a tricky point here. So, but once you get a little more practice with that, and I'll encourage you to get more practice because we've really just begun our circuitry and our electronics here, because now we're going to start looking at resistors and currents, and we're going to be still talking about series and parallel with resistors, and then we're going to put capacitors with our resistors, and we're going to put inductors, and we're just going to keep building up on our electronics here. So this whole idea of equivalent circuits where they can be is a powerful tool. All right, well, let's move on to number 4. Let's see, where is number 4 here? Number 4. This is then really getting into some heavy stuff here. This is all electric field. This is all Chapter 23. This is all Coulomb's law. Now, on the plus side, number 1 or A and B, these configurations are actually done for you in the book. We've been talking about them. So I'm hoping you can just kind of directly just jump in and do number A or letter A and letter B right away. Now, C is going to be a little taxing. I don't think that was done in an example or even on a homework one. Oh, well, we did do a solid disk. So pretty close. Yeah, that's right. We did add up a bunch of rings to get a solid disk. So this is real close. You can almost copy it directly out of the book, but you're going to have to give more thought to that. Whereas these formulas are actually already in the book, and you could actually start there. I'll probably work out the formulas just to make sure you kind of have a good review here, but there is no complete, just blindly plug and chug formula for that one. All right, so let's start with A. A says here, what is the magnitude of the electric field? Now, the definition of the electric field was force over charge. Coulomb's law was Coulomb Q1, Q2 over R squared. So if you divide it by one of the Q's, and so if you take like a Q1 here and a Q2 here, the force between them, but if you kind of remove mentally number 2, this is saying what is the electric field at point number 2. So number 2 gets removed because the field comes from number 1. And so my first little formula here, you don't need to go through these steps to derive the formula. You can just plug this in, 9 times 10 to the 9th, and the units would be Newton meters squared over Coulomb squared for Coulomb's law. Charge number 1, it says it is a 35 microcoulombs worth of charge. I think that's what I said here, yeah. And divided by, and what does the problem say? What is the magnitude of the electric field 10 centimeters away from a 35 microcoulomb charge? I'll put a coulombs here. We've got to be a little careful here with our units again, because it says 10 centimeters, but Coulomb's constant is in meters. So I'm going to put a 0.1 meters, and so one of the meters cancels off, one of the coulombs cancels off, and we get left with newtons per coulomb. And grabbing a calculator, 9 times 10 to the 9th times 35 micro divided by 0.1 squared, coming up to be 3.15 times 10 to the 1, 2, 3, 4, 5, 6, and 7. So 10 to the 7 newtons per coulomb. Yay! So, like I said, that one, hopefully you saw that one, and that gave you a good start to this one. So, okay, that's easy. That's just plug and chug right out of chapter 23. And then likewise, we've done the ring for a while. It was Coulomb's constant times the total charge on the ring times the x distance on the axis divided by the radius squared and the distance squared to the 3/2 power. So feel free to start right there. That's, again, a good place to start, maybe just for a review and hopefully not taking too much time. But maybe we should talk about, deriving this. And so the derivation went something like this. If you have a ring and you're looking at some distance along the axis of symmetry x, you're trying to find the field at point P. The logic goes something like this, that there would be a charge up here, and that would make an electric field kind of pointing off in this direction. If we give it a radius of A. But the argument continued that there would be its symmetric twin on the other side. And so the electric field from that little chunk of charge would be pointing upward at kind of this same angle, if we call that angle theta, which I guess would make that a theta and that a theta also. And that a theta also. And then the vertical components would cancel off. And so kind of the easy step is to say the field in the x direction is 0. I'm sorry, the y direction is 0, but the x direction, they add up together. And so the x direction does not equal 0. And that's where the real work begins. And so we can do this. What is the total field in the x direction? You might say that would be adding up the x component of each of these as you go all the way around the ring and add up the fields from it. And you could even argue then, well, the x component would be the magnitude. So if this one's sticking out, we call it dE for the magnitude, then we would multiply it by cosine theta. I guess this is kind of a physics 121 step where we take our vectors and we want just the x component. And so we want two adjacent of theta. So this is dE, the magnitude of it, and then cosine theta. Now, the dE, that really comes back to this. This is kind of where we argued conceptually, and hopefully you kind of got the idea. It's not an easy one to calculate, but we could technically get the electric field from any shaped object by just saying we're going to take that object and break it into small pieces. And we know the electric field from a small piece, and we just have to add them up. And that's what this integral is doing. And so that's the conceptual idea. Of course, we want components, so that's why we have this cosine theta. But the magnitude of it then would be Coulomb's constant times a little chunk dq. So if I'm thinking of each of these little chunks as a dq, then I've got something that looks like that. And now, if we continue on here, and I'm going to jump down to the denominator, the r squared is the distance that little chunk is away. And so it would be this distance here. This would be the r. Now remember, this is the x, and this is the radius a. So using Pythagorean's theorem, if we took the a squared and the x squared, we would get the r squared. So the sum of the square of the legs equals the square of the hypotenuse. So r being the hypotenuse, and the a and the x being the legs of this little triangle right here. And so that is our r squared. Now, cosine theta might be nice to view this angle. Cosine theta would be the adjacent, so that would be the x over the hypotenuse, which, again, using Pythagorean's theorem, would be a squared plus x squared, and then raised to the 1/2 power. So this now becomes Coulomb's constant times x times dq over a squared plus x squared to the 3/2 power. Okay. And this looked like this was going to be a hard one, but fortunately is not. Because as you look at this and you add up all the points along this ring, they're all the same x away, and they're all the same radius. So all these things pull out in front of the integral. The k, the x, the a squared plus the x squared to the 3/2. And so all you have is an integral of dq. And that one can just be interpreted as adding up all the charges, which is going to give you the total charge on the ring. So I can just put that right here is just the total charge on the ring. Now, like I said, you probably shouldn't take the time during the exam to rederive this. You've got a lot of work to do on Part C. But I thought I would just review this for anybody who's kind of interested. And time-wise, we're doing really well. We're way ahead of a test pace. We've already done 3 problems, and we're only an hour and 2 minutes into the video here. So I would again say that for the exam, don't do this step, just write out that boom. And for the exam, don't even do these, just, hey, these were already worked out, just plug and get those in. And use your time for Part C. So that's where we're going to do a little more work on Part C. So let me get an answer here before we move on to Part C. So this would be 9 times 10 to the 9th. The distance away, I believe this, try to keep the numbers the same so it wouldn't have to keep track of the difference between A, B, and C. It was the geometry that was the real part of the test. 0.1, okay, so 0.1. And the total charge is still 35 microcoulombs. And then down here, we have a radius of 0.05, the radius of 5 centimeters, and a distance of 0.1 squared to the 3/2 power. Now, before I put this number in, this might be a good place to pause, like I had mentioned before. We saw this back on, I think it was problem 2, where we went from a point to a rod. We've really done the same thing. We've taken the charge from a point, and now we spread it out and made it a ring. And the ring actually makes the electric field further away than if it was a point. So A, all the charge was at that point, but making it a ring, it's further away. And not only is it further away, but as we showed here in this diagram, it angles down from charges on the top, but angles up from charges on the bottom, and there's some cancellation going on. So for both of those reasons, the fact that we get some cancellation and the fact that we're further away, we should expect the electric field to be lower here at point P than it was at the same distance away in problem A. So let's see what happens here when we put in our numbers and see what we get. And I'm going to do the denominator first. 0.05 squared plus 0.1 squared, enter, raised to a power of 3/2. So there's the denominator. I'll keep that in my calculator here and just go 9 times 10 to the 9th times 0.1 times 35 microcoulombs, and then divide by that last answer, and we are looking at 2.25. Let's see, 1, 2, 3, 4, 5, 6, 7 times 10 to the 7 newtons per coulomb, and that is, yay, right here, a number that is lower than what we got in A. So I'm feeling real comfortable about that one, plus what I derived matches what's in the book. So, yep, feeling real comfortable with that. And so that would be A and B. But again, let me just say, hopefully A and B went really fast for you. Hopefully you just put in that number and, straight from that formula, plug and chug into there. But the one that's going to make you now think here and really understand the physics is going to be this step. So what do we do about this annular ring? Well, I'm going to put it this way. I'm going to say, think of this ring, or this annular ring, as made out of a bunch of rings. And so maybe the first ring looks like this, and the second one is a little bigger, and the next one is a little bigger, and the next one is a little bigger, and the next one's a little bigger. And then maybe I'll color them in so you can kind of see that I would have an annular ring by adding up a bunch of microscopically thin rings. Okay? And that's exactly what I'm going to do. I am going to say, let's get the electric field. I'll call it electric field total. Maybe I'll just put AR for this annular ring. And so here's this annular ring here. And I'm going to then say, let's add up the electric field from a bunch of rings or a bunch of hoops. Now, each hoop is really, really thin. So maybe in a different color, if I didn't, well, made it too dark, so maybe I'll just do, here's the inner radius, which the diagram calls R1, and here's the outer radius, which the diagram calls R2. I'll just kind of imagine a ring of some size that's between R1 and R2 and kind of draw it in green. And that's what I mean by here, is the electric field from that ring, and then I'm going to add up all the rings to make the annulus, or annular ring. All right, so the annulus is the ultimate shape here. And I got to add up a bunch of rings. And again, this is where it's probably best, to not have taken the time to derive this, but to then use our understanding and to copy that formula down. But I'm going to pause here because looking at this formula, which is for a ring, this is the total charge on the ring. if you make the ring thinner and thinner and thinner and thinner and thinner and thinner and thinner, something in there goes to 0. Something becomes the D what? And I'm trying to emphasize it is the charge on the ring, which we usually use a lowercase q. I'll still spell out ring. I know in this formula I put an uppercase q for the ring. But if you let me change that to a lowercase and then still leave the word ring, hopefully you'll see that I'm still talking about the charge on the ring. But I want to emphasize that something is microscopically small, and that's what we need when we put in our calculus. Something's got to be microscopically small. And I must say, when we were first doing these in chapter 23, and hopefully now that we've had 6 weeks of experience, you're getting the idea that it's not automatically a dx. Now, I know it's tempting because so often we, have learned in our calculus class about this dx, but I want to emphasize that in your calculus class, the x meant some variable. It did not mean x in space, whereas what we're doing here is our x means an x in space. So I don't want it to be that variable. I want it to be whatever variable gets small. And I got to figure out which one that is. And maybe a picture helps because, drawing it on its side and extending it out, you can see that if you mentally think about these rings getting thinner and thinner, the distance x is not what goes to 0. In fact, every ring has the same distance x. And for that matter, the A, which is the radius of the ring, is not the thing that goes to 0. When you start making it thinner and thinner and thinner, maybe better in this picture, this is still the R. The R doesn't go to 0. If R went to 0, then the ring would be a point, and you wouldn't be adding up a bunch of rings of different radii. So it's not the X, it's not the A. It's because they get thin, it's the charge on the ring. So that's a big step right there. And in fact, I'm going to do something that I hope is not confusing. I'm going to just change my A to an R. Just because it's a little hard for me to see A as being a variable. And so calling this a ring of radius R instead of A, I kind of like a little better. And so I'm just going to replace the A symbol with an R symbol there. And then say that, okay, what I'm going to do is take a ring that had a radius of R1 at first and keep getting bigger until they get to radius R2. All right, so that's going to be my variable. So I really want something up here to be a dr. That's what I really want. So how do I do that? Well, that's where, again, charge density comes into play. And so like we did in number 2, where we said the charge density is lambda, although we didn't really do too much with that, we could say that you could talk about a little bit of charge over a little bit of area, or the whole charge over the whole area, whichever way you want to do this. Now, here's why I want to do that, because I really want both. Somewhere in the problem, I want to deal with both of those. In other words, right now, I'm talking about a little bit of charge on a ring. So if I think of this little dq as the charge on this green ring, then this would be the area of a ring. And so I could replace then the dq of a ring here with sigma dA of the ring. And that can be helpful because the area, I forgot my 3/4, the area of a ring, 3/2, sorry, 3/2. The area of the ring, if you kind of imagine this green coloring here, kind of cut and stretched out, it would have a length of 2 pi r. And it would be microscopically thin of dr. So that's how we got our dr. And that's why I was saying, that's why most students are tempted at this step because they see an x to say dx. But we really don't want an x. X is the variable along this way. We want the ring thinner. We really want a dr here. And so that's the big step. Now, on the other hand, sigma, we're probably going to need that later on when we do our calculation. And so maybe I'll get that number sigma, because sigma would be the total charge over the total area. So let's come back to the problem. The problem does say that the total charge is still this 35 times 10 to the minus 6. And it's spread out over this annular ring. Now, this ring then would have an area that would, I guess, look something like this. Pi r2 squared minus pi r1 squared. Because this is the area encompassed by the big radius, and this subtracted off the little radius, or the inner radius. And so that would be my area. And let's see what I have here for my number. So let me do the bottom here. This is the pi times the bigger radius, which is 0.04 squared. And I'll subtract off the pi times the 0.02 squared. Okay, so there's my area. So if I take the 35 microcoulombs and divide it by that last number, we're looking at 0.00928. So there's my charge density, my surface charge density. And I think I'm going to need that real soon here. All right, so let's come back here and keep working on the problem. Because now I finally have gotten this idea that I'm adding up a bunch of rings, and I changed the dq to a dA, and then the dA to a dr. So now I can actually do my integration. Things that don't change, I'm going to pull out in front of the integral. And got to be careful. Again, understanding the symbols here, the x doesn't change, right? The x is how far are you away on the axis of symmetry. And so as we get different rings of different radii, they all have the same x. So that's a constant. The charge density is a constant. And of course, the 2 pi and the Coulomb's constant is all there. And so what we have is an r dr over r squared plus x squared to the 3/2 power. And so now we're going to go from our small radius of 0.02 to 0.04. And then so now we got just some math to do. And it looks like it's an integral. It looks like this is the derivative of this. So this is a perfect recipe for a u sub. So let me put u equals to x squared plus, or r squared plus x squared. So du is 2r dr. So that this would be a k, an x, a sigma, a 2 pi. And then this would be an integral of, and so the r dr can be replaced with 1/2 du. And then downstairs, I would have u to the 3/2 power, but I'm going to go ahead and move it upstairs. That's the neat thing about the u sub here. And now I've got a pretty easy integral to do. This is Coulomb's constant x sigma 2 pi. Here's the 1/2 again. But when you do an integral of a power, you add 1 to it. So that is u to the negative 1/2. And you divide by the new power, which actually is great because this 1/2, I was tempted to cancel with that too, but I like it canceling with that half. And I'll just put then the negative in front of the k. So negative kx sigma 2 pi, and then I have my u to the 1/2, which I will then replace. I'll put it downstairs, so it's a plus 1/2, and I'll put in then the r squared plus the x squared, and evaluate it from 0.02 to 0.04. All right, so we're about to get a number here, but let me pause and say, what kind of number do I expect? Well, I would argue here that this annular ring is actually annulus, whatever, same thing. What you have here is all the charge here is spread out. Some of it towards the middle, not all the way at the point, but none of it as far out as B. So in B, as we said earlier, the charges out here would be further away than the 10 centimeters was back in part A, and they tend to cancel each other off. And so we have less of that going on here. So in this one, with the rings in close, not only are they closer distance to point P, but they're not angled as much and don't cancel each other off. So I would expect this annular ring to give me a field stronger than what we got in B, but smaller than what we got in A. So keeping that in mind, in A, we got 3.15 times 10 to the 7. So I expect it smaller than that. But I expect it bigger than 2.25 times 10 to the 7th. So let's see what we get. All right, so grabbing my calculator here. Maybe I will do this calculation in its two parts, because if I put in the 0.04 squared plus the 0.1 squared, oh, and I think I forgot the 1/2 here. Here we go, 1/2. And hit enter, and then take the square root of that, and take the reciprocal. This first one is about a 9.285 minus, and then if I put in the lower limits, that would be 0.02 squared plus 0.1 squared, enter, and then take the square root of that and take the reciprocal of that, and this is about a 0.9806. All right, so let's see if we can put all this in here to our calculator. I will, can I go up there and get that 298 minus this last one, and so that's the difference. Let me multiply it then by this, which would be times a -1 there, times 9 times 10 to the 9th there, times the x, that's the 0.1, times the charge density, or do we do that up here, 0.00928, times a 2, and then finally times a pi, and I get 2.73 times 10 to the 1, 2, 3, 4, 5, 6, 7. And did that meet my expectations? Was it less than A? Yes. Was it more than B? Yes. Okay, good. Ta-da! So definitely part C is a hard one. So hopefully you had no troubles doing A and B. They were really plug and chug. But C is asking a lot. So don't beat yourself up if you had troubles with C. Completely understandable, but hopefully you are taking the time to teach yourself and go through this video real carefully and say, okay, how would I do it right next time? Like on the final exam, you know, or whatnot. So, or maybe even just next test where I need it in order to do this problem, because, you know, physics always builds on itself. You've noticed that in problem 1 and 2. If you had forgotten your physics 121 stuff, hopefully you saw that on the homework and you refreshed yourself doing the homework on that. But, you know, same thing's going to happen later on. We're going to be working in chapter 30 and go, oh, remember how do we do Coulomb's law? And hopefully the answer is, oh, yeah, I do. Or no, I don't. I need to go back and look at it. So this is a good one on the fundamentals of Coulomb's law, and a good hard one here on C. All right. Well, and finally, hopefully I haven't been talking too much. Usually I find that maybe a good time is, you know, taking the same time that I talk about it that you did on the test is pretty good, because if I can talk about it, say all these things, and do a bunch of extra stuff, it's about the same time that you would do during an exam. All right, but we're really good with time. We've got way to go. We're only an hour 25, and you guys had 2.5 hours. Of course, some of that is to scan it still too. So we still got an hour and 5 minutes to finish up this last problem, and it won't take us that long. So, where is the last one? And the last one hopefully looks a lot like the homework problem one. Yeah, this was one of the homework one. This was kind of a reward for those of you who actually did every piece of the homework and actually worked it through. Now it's slightly different than the homework one. The homework one, for those of you who didn't recognize it, this would be rho cx squared on the homework, but it's 4 on this one, and then also on the, oh, I'm sorry, this was not the homework. I think of the practice test, or maybe it was homework. I think it was practice test, because the practice test found it outside the slab. And so all I did was switch it up a little bit. I changed the power so you'd have to do the work, and I said inside instead of outside. So a little, just a hair different, enough that hopefully you reap the reward of going through it, but it also, you know, gives it as a test quality to say, are you really following what's going on? And so one of the first things to do is to recognize that because of the symmetry, this is a really good one to do with Gauss's law. And like I said, if you've did the practice test, you saw the Gauss's law stuff right away. So hopefully that clicked first. So I'm going to write that down first. Plus, we haven't had a Gauss's one yet, and that was a big piece of our first chapter. So it looks like this is the only one from Gauss's law here. So remember, Gauss's law is this very useful technique, takes advantage of a lot of symmetry here, and so I'm going to kind of draw the slab here, and we're going to be inside, so maybe I should have made this slab a little wider. So let me take a wide slab here, and maybe here's the axis in the middle, and let me just draw then a Gaussian surface. That is this cylinder shape, that each of the end caps have an area of A, and then the area of wrapping a round is the area of a face. And for those of you who've joined me in my Zoom, and I think some of the videos, I like to kind of just roll up a little sticky one, and so you can get a little more of a three-dimensional view here. But this is that Gaussian surface. So we'll call the rounded part the face, and we'll have the caps of them. And so we've got a left cap and a right cap here, our end caps. And there is our Gaussian surface. But one of the things that we emphasized big time, and hopefully you did it here first, was to take the dot product and then break this apart into its 3 areas. So I'll call this area 1, and this one area 2 over here, and then then the face part of it, area 3. And we have to have a closed surface for Gauss's law to be valid. But again, like the practice test one, whether we're drawing a cylinder that goes outside or inside, there's some symmetry here that it's the same argument we could make. And these lines of symmetry are them. And so we know the electric field then is along the axis of symmetry of this cylinder. And since the charge is fourth power, that means it's equal on both sides. So if you flip it, it doesn't matter which way it goes. So the electric field would be pointing outward from our Gaussian surface. In other words, it's pointing left on the left-hand surface, but it's pointing right on the right-hand surface. And so that means this angle here would be 0 degrees, and this angle too here would also be 0 degrees. I'm not saying the electric field points in the same direction, because the normal changes direction. So the normal over here on the left face points left, and that's the same direction as the electric field. And the normal here on the right face points to the right, which is the same as the electric field. So both of those have an angle of 0. And along the face, then, we've got 90 degrees, which cosine of 90 is 0, and so that one just drops away. And then, of course, we can see both of these are the same, so we'll just double these up. And so that's 2. Then our argument goes something like this, that if you were to put this Gaussian surface, equal on both sides, whatever the field is on the left matches the field on the right. So that's why we double it up, and it's a constant over that field. So we can just factor out the E. And then all we end up with then is an integral of A on the left face, or the right face, since we're saying they're the same. And so that would just be the area. So that's how you would do this side of the equation. Maybe the harder one here, well, I don't know. I guess I'd probably say it's easier, but we haven't done it as much. So we did a lot of this. So this is harder, but since we've done so much of it and focused on it, hopefully that was something that was well learned and ingrained. But here we would have something that I would do this. I would just put the 1 over the epsilon naught first, and then say, okay, how do I get the charge inside of the Gaussian surface? And I'm going to just say, well, I would add up all the charges. Okay, so I'm going to add up all the charges. And then this is where a lot of our density comes into play. This would be the density times the volume, where maybe over here I'll put density is equal to the charge over the volume. And so a little bit of charge over a little bit of a volume. Now, you can think of then this little volume maybe as being little discs. Maybe you can even think of this as being a stack of coins on its side. I think I got a nickel sitting over here. Maybe I should get a stack of nickels. But here's a coin and 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 a coin. And so as I get a stack of them, this volume then would be the little volume of this coin. And so this would be the density, and the volume of this coin would be the area of this coin, so A, and if it's a cylinder, this all the way through here is the same cross-sectional area, so this area here is the same as the other side of the equation, and then it's thickness d dx. And then, of course, what's nice about that is we can pull the A out in front, and we can actually then put in from this problem what the equation is for the density. And then 2E, right, something like that. And to finish things up then, I'll put a 2EA on this side, and so I have an A over epsilon naught here, and even a C, I'll pull that out in front. And then I have this integral of x to the 4th dx. And at this point, I needed to do the total charge inside of the Gaussian surface. And here's the only thing different between here and the practice test is the practice test, since we were on the outside, we would only want to add up from one side of the slab to the other. That would be the charge inside. But here, we don't want to go all the way to the edge of the slab because we're looking at a Gaussian surface that is smaller than. And so the charge inside of the Gaussian surface is not all the way to the edges of the slab. So if we had set this up from, x to x, or negative x on the left and positive x on the right, we would then be getting the electric field at point x. So it's probably best to say we're going to go from a negative x and we're going to integrate then to a positive x. Yeah, that's probably the best way to do it. Now, of course, we could also say then that what am I looking for here? We could say that we only do this half of it, 0 to x, and double the charge. So I think that's what I'll do here, is I will go from 0 to x and double the charge. So, I'll put it here, 0 to x and double it. In fact, as long as I have the 2 in the A and the 2 in the A, I'll cancel that off. And so now we have E, and we have the C and epsilon naught. And then I would have x to the 5 over 5 evaluated from 0 to x, which doesn't really change anything. We just have c x to the 5th over 5 epsilon naught. Yay! And so there's the equation for the electric field. Give me any value of x, like x equal to 0, I would get 0, and as I moved out here, I would have some value for the magnitude. And I should emphasize back here when we took this dot product, this is the magnitude. So even at negative x's, I wouldn't want to get a negative number here. Although technically, I guess negative does point in the negative direction, so we could kind of put in some vectors to it. But once we took the dot product, we're actually only solving for the magnitude. So hopefully, again, that one kind of matched what you saw on the practice test or on the homework, because by itself that's a hard one. But hopefully you're rewarded by your hard studies there. And there was just that slight difference in the sense that we don't want to make a Gaussian surface bigger than that, because this one be a little different than the practice test. We want the field inside the slab. And that's really the only change right there, the limits. And, well, I guess the function, like I said earlier, I gave a density of x to the 4th, whereas on the practice test it was x squared. All right, well, I talked a lot. Hopefully you got a lot out of this if you spent the whole time going through each of these problems, and hopefully you didn't try to do it in one sitting, maybe one at a time. All right, take care.